Welcome back. This is lecture number 16. In this lecture, we are going to talk about feedback control of cascaded switch mode power converters. In this lecture, I am going to talk about cascaded converter in an cascaded DC-DC converter, series connected cascaded DC-DC converter, which is sometimes known as intermediate bus architecture. In this context, I also want to introduce the notion of constant power load. Then also I want to give an example of unstable open loop system. That means a converter, open loop converter can become unstable while driving a constant power load. And then I want to tell feedback control for active damping in order to stabilize the unstable open loop plant. So, cascaded DC-DC converter, if you take an example like two DC-DC converters are connected in series, and you can see the input voltage, this is the input voltage, which is connected to it is a DC voltage, and then the first stage converter output is the bus voltage, it is called the bus voltage V bus, and the second stage converter output is the actual output voltage which is connected to the load. So, that is why the first stage converter, I will come to the point that this is called intermediate bus architecture, where the last stage DC-DC converter is known as point of load converter. Okay, I want to give an example. If you take an LED driving, like automotive LED driving, in general it has a 12 volt battery, and then you need to drive multiple LED load, because most of the recent cars are coming up with LED lighting system, which include like a headlight, tail light, fog light, there are various other lights, and they have certain different voltage ranges. Like for headlight can be in the range of 12 to 14 volt, and then there are other lights, but the battery is 12 volt. So, if you want to convert from 12 volt to 14 volt or 12 volt, they are almost close to each other, and the battery voltage can also vary. So, in such while we can use a simply buck boost converter, but it requires certain stringent performance requirement. The another thing, we also need to ensure that LED is like a constant current load. So, we need to maintain the current of the LED string. So, it is generally expected that output should have a constant inductor. That means a DC-DC buck converter can be an output where it has the inductor at the output side. So, 12 volt, where the bus voltage can be even higher, instead of 30 to 48 volt, it can be even 60 volt or higher, the intermediate bus. And the output of the LED can be roughly around 12 volt, it can be 14 volt. So, that means you need first stage converter to boost up the voltage from 12 to 30 or 48, even 60 volt, and the second stage DC-DC converter has to convert that voltage into 12 volt. Okay. So, it is a step down converter, and this kind of architecture is used for headlight application, for automotive LED. The another application is a data center. In fact, this is also true for most of the telecom sector. They have a 48 volt power supply, and telecom, there are multiple load, like you have a processor load, then you have like a communication device, their voltage can be few volt, like in 3.3 volt, 5 volt, or even roughly around 1 volt for the processing application. So, 48 volt to such low voltage in single stage, sometimes it is difficult to use a single DC-DC converter, while there are recently in data center application where the 48 volt is now become a standard, and we need to achieve the output voltage roughly around 1 volt, because it has to run or it has to supply to processor, where the processor can be server processor can be desktop computer, laptop computer, or the server computing station, where the current can be significantly high and the voltage is around 1 volt at the output terminal. That means the output load can be a processing load, which voltage can be around 1 volt, but the current can be hundreds of ampere. So, in such application, when we want to convert 48 to 1 volt, and that too are driving to a high current, then though there are recently research is going on to come up with a single stage converter, this uses isolated converter for transformer based high step down converters, as well as hybrid switch capacitor converter, which we discussed at the beginning. and the high bit switch cap architecture can be used at the input side to step down the voltage, and then it can be just simple multi-phase DC-DC buck converter. But all this architecture, but two-stage architecture still considered to be an effective choice, because we can optimize the intermediate bus voltage, and by that way we can improve both performance and efficiency of this two-stage architecture. So, this is processor load. That means, in these two application, even there are like a telecom application I told, for example, in the telecom application, that 48 volt is a common supply, is a standard, and then the load POL, that means point of load, this can be roughly around 3.35 volt or less, around 1 volt or so. For such application, two-stage architectures are generally preferred. So, I am here considering the specification, which is like a intermediate bus architecture, in which I am taking two cascaded DC-DC buck converter. The first stage is converting 48 volt to roughly 12 volt, and the second stage I am converting 12 volt to 1 volt. Okay. And in this architecture, input side buck converter is known as intermediate bus converter, IBC, and the output side buck converter is known as point of load converter, because it is directly supplying to the load. That is why it is called point of load or POL converter. Now, this is a very simple example of an intermediate bus architecture. So, this is called IBA, intermediate bus architecture. In this architecture, the first stage, this first stage converter, this is a buck converter, number 1, and there is another converter, buck converter, which include this stage. This is another buck converter 2, and this converter as I told, it is called IBC, intermediate bus converter, and this converter is known as point of load converter. Okay. So, the second stage converter is known as point of load converter, which is designed to drive low voltage high current application, and in this case the load for the POL converter is a resistive load, but it can be constant current load, many other type of load. So, typically it is either resistive load or constant current load. For the source side converter, which is called IBC, the load is a DC-DC converter itself, that means another converter. So, the IBC is driving another buck converter. So, that means it is neither a resistive load nor a constant current load, but what type of load it is, it can be approximated, that we will see. So, we want to first I want to show a MATLAB simulation case study. So, we want to consider our simulation model of conventional as well as synchronous buck converter, because in our earlier lectures I have demonstrated how to develop building block, like how to develop from the scratch a model of a buck as well as like a buck converter. We have also demonstrated boost converter example, and I have also demonstrated that a converter buck or boost, any converter can be configured either in conventional configuration where it includes a diode, or it can be configured as a synchronous configuration where both are switches, synchronous switches. Now, I want to show that configure the above, like I will take one buck converter model in the Simulink MATLAB model, and I want to cascade them in order to develop this intermediate bus architecture. So, how to do that? Okay. So, in this MATLAB example, I want to show you this is the example. Okay. So, if I remove everything, like I remove all this interconnection, for example, let us remove everything. So, initially forget about all this configuration. Okay. So, this thing will come slowly. Now, if you remove everything, We have earlier explained what is this. So, this is one buck converter. We have already developed a model for it, and I have just taken that model and I have pasted here. That means, you can simply take this model, particularly this model, you can copy it and paste it here. So, this model is nothing but the copy paste version of this, okay? That is it. But if you go inside, what you need to change here, because each converter we may not use the same inductor capacitor, because each converters their voltage and current ratings are different, and we have also discussed how to design power stage for a given input voltage, output voltage, load current specifications. So, that is why we should not assume both the converters to have same inductor capacitor value. So, if they are different, then the model structurally remains same, but only we need to update the values of the inductor, capacitor and so on. So, if you go inside, what it has 4 subsystems that we have developed. One is the inductor current dynamics, capacitor current dynamics, then a DCM logic block we have developed, then a switch node voltage block subsystem. If you go inductor current dynamics, only thing you have to change this L value 1 by L1, that is the 1 by inductance value, and that we have already discussed earlier. So, here we have taken, instead of 1 by L, I have taken 1 by L1, that means it is the inductor value of the first stage converter L1. For second stage, I will put it like L2, that is it. The other thing, if you go back to the initial condition, so I want to make separate initial condition for the first stage inductor and the second stage inductor. That means, I can put everything start from 0, but here I want to customize the initial condition. So, you see earlier it was I underscore L underscore initial condition. Now, I just put a like a number 1, because this is for the first stage converter. Now, for the sake of simplicity, I have considered the parasitic DCR of the inductor same, but you can also choose a different inductor value L1. So, this I just wanted to make it simple. So, you need to simply update this parameter value. Then, so all these things are same, there is no change here, that means these things are all changed port. Next, if you go to capacitor dynamics, what are we going to change? We need to change the value of the capacitor. Earlier it was 1 by C, now it is 1 by C1. Okay. Similarly, ESR of the capacitor, here I kept it common, but I can change it, there is no problem. And I should be able to customize the initial condition of the capacitor voltage, which is Vc. It was earlier V underscore C underscore initialization, I just put a number 1, just to distinguish between two capacitor initial voltages for the first stage and the second stage. Then what else? In the DCM enable logic, everything is same, there is no change, okay, because these are all symbol, internal structure remains same, but this enable signal which is coming from outside, that I want to make it different. The switch node voltage, we have to be careful here. What is different here? Here only difference is that this expression that we have developed earlier, that means we have made a common expression here, which is when it is in DCM enable, that means when it is in conventional configuration, we want to include the resistance of the diode RD. When it is in synchronous configuration, I want to include the resistance of the low side MOSFET, that means R2. So, that is RDS1 of the low side MOSFET. So, that means what we need to change here? I want to only change DCM enable number 1, that means this is the one particular block I want to customize at my .m file, where DCM underscore en enable, I want to number it number 1 and number 2. So, here it is number 1, so I am just updating the value. Similarly, here we can include diode drop. If it is a conventional configuration, then we will include diode drop, and that is enable 1, because it is linked with the first converter diode drop, and you can also make a separate diode drop for the first stage. That is it for the first stage, and you can make the similar changes in the second stage. If you go inside, you will see it is DCM enabled 2, and you can make diode drop 2 also. Similarly, if you go to inductor block, I want to consider 1 by L2, because this inductance, the POL converter inductance value should be different from the IBC converter, because we want to make it different. Though we can put same value from the code, but we should make it generic, so that we should flexibly design the inductor of the two different stages. Similarly, I have kept the different initial condition for the inductor current initial condition for the stage 2. The same thing is also applicable for the capacitor IC2, and same thing also true for the initial condition of the POL capacitor. Okay. So, I kept the ESR to be same, but I can make it different. Okay. Now, for the external parameter, what I am doing, I am keeping a separate DCM enable signal, because I want to run this POL converter, which is in the output side, to be, okay, let us write this is buck converter 2 and this is buck converter 1, that means 1. So, I call it as a IBC, and I call it as a POL, this is I call it as a POL. Okay. So, for the POL converter, I generally want to operate in synchronous configuration. So, I can separately set this DCM enable signal and I will set it to 0, so that it can run in synchronous configuration in most of the cases, except for the live load condition. But for the first stage, I probably may operate it in conventional configuration, when I can keep DCM enable 1 to be 1, so that it goes into a regular buck converter with a diode, and if you keep it 0, it can be synchronous configuration also. Okay, so these two are different. Now, for the first stage, input voltage is our 48 volts. So, this is the V in, which I define from the very beginning stage. So, this is the input to the first stage, and for the first stage, initially I am keeping an open loop configuration. That means, I am applying a fixed duty ratio pulse width modulation signal, in which the duty ratio I kept D1 to be D1 is the duty ratio, that into 100 is my percentage, and the time period is T1. But for the second stage, I want to operate in closed loop. Okay. So, I think this part is clear, but now I want to connect. How do I connect? You know, if we go back to the circuit, okay. So, for the first stage, if you look at this first stage, so this is the output current of the first stage, that means this is the I01, and this is the IP2, that is the input current of the second stage, and this is my I02, that is the load current of the second stage. Okay. And this is the, now for the first stage, my input voltage is 48 volt. For the first stage, my output is I01, which is nothing but the input current of the second stage. Okay. And for the second stage, the output current is nothing but it is the resistive load. So, it is nothing but the V02 by R2 R, it is a resistive load. I can use a constant current load also. Okay. Now, let us go back to the MATLAB. So, for the first stage, input voltage is V in, and what is the load current for the first stage? I told you the load current for the first stage is nothing but the input current for the second stage. So, I simply connect this. So, it is a drag and drop block. Then output voltage of the first stage is input voltage of the second stage. I just connect it. So, these are optional. That means, inductor current, capacitor voltage, we may not connect, it need not to be connected, like it is, it is not mandatory. But I should connect the load current for the second stage, and if I use a resistive load, I can simply connect this resistive load here. Okay. So, resistive load I can simply connect, and that we have explained in many simulation case study in the past. Okay. So, that means I have connected it. Now, what I need to give? I need to provide a gate signal for the second stage. Okay. And what I want to observe? I want to observe the inductor current of my first stage. So, let us connect it. I want to observe the inductor current of the second stage, that is my channel 2. I want to observe the output voltage of the first stage, that is my channel 3, and I want to observe the output voltage of the second converter, that is my channel 4. And same as earlier, what is this? So, this is nothing but the result that is actually getting stored into the workspace, okay? That is getting stored in the workspace. Now, my connection is over. Now, what I am going to do? So, yes. Now, I want to operate the first stage in open loop, and that is already connected, but I want to operate the second stage in the closed loop, and this is the current mode control, and which I have already demonstrated in my earlier presentation. So, this is my Vref2, the reference voltage 2 for the second stage. This is my V02. So, I can simply change it V02, and this is my IL2, the inductor feedback for the second stage, and let us connect this. So, this is the output voltage feedback, and this is the inductor current feedback. Okay. So, everything is now set, and the gate pulse will go to the second stage. So, now we are operating the second stage to be a current mode control. Okay. Second stage is current mode control. Now, so let us do not consider this block at this time being. Now, so first stage in open loop and the second stage in closed loop, and what are the parameters that we have set? Let us go back to the MATLAB file. So, we have considered a parameter file where for the first stage IBC, I choose an inductor to be 20 microhenry because it is operated at a lower switching frequency. So, I will come to the specification part. So, this is the interconnection part, and it is over. Now, go back to the presentation. So, we have configured a cascaded DC-DC converter, which is IB intermediate bus architecture using our previous model. Next, dynamics of the IBC converter we want to check. So, as I said, the intermediate bus architecture, it consists of two converters. One is intermediate bus converter, another is the POL converter. Now, the IBC, the input voltage is high because we are talking about roughly around 48 volt, and here we are talking about 12 volt, and here we are talking about 1 volt. Okay, that is our nominal voltage. So, for IBC compared to POL, it is designed for high voltage low current, whereas the POL converter is designed for low voltage high current, and this POL has to cater the requirement for a processor, and the current can be some hundreds of ampere, but since we are only using one phase, so we will go up to 20 ampere is my nominal current for this current. So, this is my I02, this is my nominal current. So, this is my I02 is my nominal value. So, it is low voltage high current application, and the requirement of transient requirement is extremely fast in the second stage, okay, whereas the first stage is used to convert from high voltage to an intermediate voltage. So, the purpose of the first stage need to be very efficient, at the same time it should be reliable, because it should also try to provide some clean output voltage at the intermediate bus. Okay. The second stage, which is the POL converter, it has to be very fast, because even I am just showing one phase where only 20 ampere is the nominal current, but typically this kind of architecture, the output has to handle around more than 60 ampere, or it can be several hundreds of ampere. That is why this stage has to be very fast to meet the stringent performance requirement, and it is often operated under current mode control. Okay, so it is often operated under current mode control because it requires a very fast transient response. At the same time, when you go for multiple phases, we need to do current balancing among the phases, and the current mode architecture is very popular for the balancing of current in between multiple phases. Okay, and the first stage, which is operated at higher voltage, and we have discussed about the losses, and what we we have learned from the previous lectures that if the input voltage is high, then the switching loss can be significant if the switching frequency is high. So, that is why for high voltage DC-DC converter, we should not go for very high switching frequency, because the switching loss can be very high, because switching loss is proportional to the input voltage, okay, and of course, it is proportional to switching frequency. So, in order to reduce the switching losses, the input side converter, which is known as IBC, is operated at a relatively lower switching frequency, whereas the output side converter is operated at much lower voltage. So, you should operate at a much higher switching frequency, because then we can reduce the value of the inductor, capacitor, parasitic, because these POL converters are sitting very close to the actual processor, where the space is also a constraint. So, we need to make sure that these converters are very high power density, that means very smaller footprint, and that is why we need to operate at a very higher switching frequency. Okay. Now, next part, I want to create a simulation case study, where as I discussed that IBC is operated at a much lower switching frequency, because it is connected to the higher input voltage, whereas POL is operated at a higher switching frequency, which is in this case IBC is operated at 100 kilohertz and POL is operated at 500 kilohertz. So, our T1 is nothing but 10 microsecond, and our T2 we are taking here is the 2 microsecond. In fact, this specification is I have used, which we have considered so far for a normal, like a standard buck converter, where we consider 12 volt input and 1 volt output. Now, I want to show this POL converter is operated under, so this is operated under current mode control that I have discussed. This is operated, and it is operated at a very high switching frequency. So, for IBC, this converter resembles a constant power load, and we want to see whether it really resembles as a constant power load or not. Okay. So, before coming to that, that means before you go to the simulation, it is well reported in the literature that sometimes this two-stage architecture can be simplified as by keeping this IBC here, this POL can be replaced by a constant power load, because this POL is operated at a higher switching frequency with using a current mode control. So, it is very tightly regulated, and that is why IBC will see it is like a constant power load, where if IBC is driving a constant power load, then there can be negative incremental impedance effect, and that may lead to stability problem while driving a constant power load. But we need to first verify whether a two-stage full scale switching converters can resemble a switching converter driving or a buck converter driving a constant power load or not. Let us go to the simulation. So, as I discussed that for the first stage converter, the time period is 10 microsecond and the reference voltage for its output is set to 12 volt, because we want to achieve 12 volt as the intermediate bus voltage. The inductor voltage is kept, inductor is 20 microsecond I have kept, and the intermediate bus capacitor is set to 600 microfarad. And we want to see if we change this value, because this value depends on the ripple characteristics, but we can change some higher and lower value. But I want to show this value of intermediate bus capacitor has a significant strong influence on the stability of the cascaded system. For the POL converter, inductance is set to 0.5 microhenry, and which I kept the same as our earlier configuration. The time period is 2 microsecond, capacitor is 200 microfarad, which we have already designed earlier using a power stage design criteria. But in this converter, we kept the reference voltage to be 1 volt, because we want to achieve 1 volt output. Overall input voltage is 48 volt, which is the input to the IBC, and we kept the parasitic to be more or less same for both the converters. This is for sake of simplicity, but as I said that you can take different parasitics also. Now, we want to first run that if we go to the Simulink model, we want to run the POL converter using open loop, closed loop using current mode control, and the IBC converter using open loop using a duty ratio D1, and I will say what is D1. Okay. So, now in this MATLAB file, I have discussed all these MATLAB simulation file. The process is same. So, where we will call this parameter file, which is stored here, all the parameter value. Then I have set D1, which is a nominal duty ratio, and that is the output by input for the first stage, and the output of the desired output of the first stage is Vref1, which is set to 12 volt, and the input is 48 volt, which I discussed. For the second stage, though it is not required duty ratio because we are running in closed loop, but for sake of completeness, so D2 is nothing but Vref2, which is the desired output voltage of the second stage POL converter, and input to the POL converter is nothing but the intermediate bus, but our desired value of the intermediate bus is Vref1. So, the desired output voltage is D2, desired duty ratio is D2 for the POL converter. Now, I am considering power level of 20 ampere because my POL output voltage desired value is 1 volt, and I want to operate the POL current converter with a nominal current of 20 ampere, because for single phase this is somewhat standard. So, 20 ampere into 1 volt is a 20 watt. So, what should be the resistance, because it is a resistive load, so it will be V reference 2 square by P0. Okay. Now, if I go back inside this current mode control, and this block is already explained, but we have also discussed the current mode control does not require a PID controller, a PI controller is enough, but we are using a default PID structure available in the MATLAB, where proportional gain, integral gain we are defining from the MATLAB, and the derivative gain we are setting to 0 from the MATLAB itself, and we are setting some initial value of the integrator. Okay, so you can keep it 0, there is no problem. Okay, now let us run the simulation and check. So, if we run the simulation, let us go to the simulation result and see. So, for all the simulation result traces for the inductor current, I have considered the red trace for the POL inductor current and the blue traces for the IBC inductor current. Okay. So, let us go back and check. Okay. So, here I am showing, if you see the waveform, the top one is the POL inductor current, and since I want to regulate the POL output to 1 volt and my desired output power is 20 watt. So, my desired output current is 20 ampere. So, you can see the average inductor current is here closely 20 ampere. That means, we are achieving that desired current using this POL converter. In the IBC converter, you can see the switching frequency or time period is 0.01 millisecond, that means 10 microsecond, whereas there are 5 such cycle within 1 cycle of the IBC. 5 cycle of POL inductor current is same as the 1 cycle of the IBC inductor current. So, POL converter is 5 times faster and its time period is 2 microsecond, that can be shown from here. So, these are the inductor current. Then if you go to the output voltage waveform, I will show you. Again, the red traces indicate the inductor current waveform of the IBC POL converter, that is nearly 1 volt. It is not coming, it will take some more time, but it is almost 1 volt average voltage. Okay. Whereas, if you see the average output voltage of the IBC converter is roughly 1 volt, 12 volt, because we want to achieve to a desired voltage of 12 volt, but since it is running in open loop, it may not maintain 12 volt. But what is important here to observe that the POL converter output voltage is somewhat oscillatory, and if we closely watch this oscillation seems to be decaying. That means, the amplitude of oscillation is slowly decaying. It will take time, but it is decaying very slowly. Okay, so this is one simulation configuration I am running. Now, we want to take the second one. That means, we want to take, if the second case we replace this IBC, a POL converter, by a constant power load, then can we get identical result? Right now, whatever we have simulated, we have used two DC-DC converter, both POL and IBC, and POL was operating under current mode control and IBC was in open loop. Now, I want to repeat the experiment where IBC still remains in open loop with the same configuration, but POL converter, closed loop POL converter is replaced by a constant power load, and which is the magnitude of the constant power is 20 watt, that we have discussed. So, in this case, if we go back to this, now what we are doing, the second stage we do not want to use anymore. That means, we want to remove this load current. What is the load current? It is now the constant, it is coming out the constant power load. And what is the amplitude of the constant power? That means, we want this constant power P0, this to be P0. It is my constant power, which I have already defined from the simulation file, and the output voltage is here. And if you go inside, it is just a simple MATLAB function file where the load current is nothing but power by voltage. So, since the power is constant, so if there is any variation in the voltage, and then it will be, current will also vary. So, it is a nonlinear load. Okay. So, it is just a function file. Now, for this case of simulation, we want to repeat, that means, we want to retain the earlier traces, but we want to use dotted line now, because we want to check whether they are exactly identical or not. Right now, we are not using earlier simulation, we are now considering the IBC converter open loop, which is same, but POL converter is replaced by a constant power load that we have discussed here. Now, it is a constant power load. Though it is running like this converter, the second stage, but I want to evaluate the dynamics, I want to investigate the dynamics of the IBC, which is not connected with the POL converter anymore. Okay. So, if I run it, now this condition, everything like initial condition, everything I kept same, and you can see the output power is 20 watt, and now it is running under constant power load, and where we want to focus on the waveform of the IBC, not POL, because in this case POL is not connected to the IBC. Okay. Now, let us go and check. So, here you can see there are two traces. The one trace is this trace is the output voltage waveform with POL constant power load. That means, if I zoom it, if I take one particular cycle, okay. So, this waveform, if we go inside, that means, if we take a closer look of this, you can see there are multiple switching with discontinuity. This is the case when the POL converter was connected, because the POL converter input current was discontinuous. As a result, it actually injects some discontinuous voltage jump, because there is an ESR in the capacitor of the intermediate bus, and any discontinuous current in the capacitor current will actually cause a discrete jump. So, that is why you can see there are 5 cycles within one cycle of POL IBC. So, if you see, this is the one cycle of the IBC from this 1.5 to 1.51, one complete cycle of the IBC switching cycle. In this cycle, when we are considering simply POL converter, this discontinuous ripples are not appearing, because its current is not discontinuous, output current is not discontinuous. But in case of actual switch simulation, when the POL was connected, you can see there are discrete jump, and these discrete jumps are due to the discontinuous current of the POL input current. and that will appear at the capacitor of the IBC and which has a ESR. So, there is a discrete jump which happen in every switching cycle, every switching transition of the POL converter, and that will happen 5 times in a cycle, and that you can clearly observe from here. If you take from here to here, there will be first 5, 1, 2, 3, 4, 5, and so 5 2 times. Okay. But what we want to observe, that means if we take the two output traces, the one with actual switch simulation of the POL and the other POL is replaced by a constant power load, the waveforms are not exactly identical. They are not exactly identical because it is well reported in many literature that all investigations are carried out simply by taking constant power load. But if we go to actual switch level behavior, they are very much different, and in some time the complex nonlinear behavior in the POL can cause stability problem in the IBC, and which will not be reflected when you are replacing that POL with an actual constant power load. So, in average sense, in low frequency dynamics, they are somewhat similar. That is why if you see their average dynamics, they are close, but they are not exactly identical, but they reasonably capture the average behavior. The profile are somewhat similar, but with slightly different amplitude. If I go to the inductor current waveform, if we are interested in this inductor current waveform, so you can see the inductor current waveform are not exactly identical. There is a slight difference. Again, the cycle by cycle behavior, they will not be same, but in average sense the profile has some oscillatory property, and which is also true here, which is also reflected here. That means, if we come to our conclusion, our assumption that this POL converter can be a current mode control closed loop POL converter can be replaced by a constant power load, this assumptions is valid in the sense of small low frequency behavior which can reasonably capture the slow scale instability of the IBC converter, but it does not capture the switching dynamics and nonlinear phenomena of this two stage converter. Okay. So, the simulation case study, two separate converter we have operated in 100 kilohertz and 500 kilohertz. In case 2, keep the IBC configuration same, and we have replaced a constant power load, and we saw that their behavior are somewhat close in the average sense. Now, one thing we want to observe before we do closed loop control, that means what we found, now we want to go for actual switch simulation, no actually constant power load. This was just for sake of analogy, because it is there are a lot of research papers where they simply consider this configuration, but we do not want to take this configuration anymore, but this can be used for low frequency stability analysis, and which can be reasonably which can capture the low frequency stability behavior property. Now, we are going to actual switch simulation, and we want to investigate that what will happen if that means we saw using two buck converter under this configuration, the IBC was operated in open loop, and we saw some slow scale oscillation, but the oscillation was dying out. But we want to change the parameter and see what is the impact. Suppose if we reduce the intermediate bus capacitor from 600 microfarad to 200 microfarad, and if we run the simulation and see whether the change in IBC output capacitor can affect the stability or not. This is particularly important because we sometimes need to keep a smaller capacitor in the bus architecture, because this will so we will come to the discussion, because this smaller capacitor of intermediate bus architecture can help to quickly change the intermediate bus voltage, which can be used to optimize the performance and the efficiency of the POL converter. This is very much useful for trade off between performance and efficiency in the two stage architecture. we saw if we reduce the capacitor value, then the stability of the IBC also get affected. That means, IBC now the oscillation is slowly increasing. That means, this is a typical example. If you take the average waveform which behaves like a linear system phenomena and the oscillation is increasing exponentially, and this is a typical case for an unstable open loop plant. That means, here IBC is driving a POL converter and POL converter is tightly regulated using a current mode control, and since it resembles to some extent the constant power load, and when a open loop buck converter driving a constant power load, so when you are reducing the intermediate bus capacitor, the open loop converter become unstable, and as a result the output voltage is slowly, the oscillation is happening and this oscillation amplitude is slowly increasing. Okay, and if you wait for a long time, that oscillation will grow up significantly and it can damage the converter and the device, and it can lead to complete collapse of the closed loop two stage converter. Okay. So, now I also want to see whether there is any impact of the inductor. That means, now we are going back to the capacitor. Suppose if we increase the inductance value of the first stage, because we want to further increase efficiency by increasing inductance value, so that the ripple of the current can be reduced and conduction loss can be improved. I mean, although it is not necessary, but we want to investigate whether this inductor has any effect or not. So, in this case I have changed the inductor value of the first stage from 20 microhenry to 40 microhenry, where my capacitor is restored to 600 microfarad, because you want to see the effect individually one by one. So, you can see here, if we increase the inductor value of the first stage converter, it is somewhat oscillatory, slowly increasing, but it is somewhat oscillatory, and this may lead to something called limit cycle oscillation. Okay? Because there is a sustained oscillation, and but we need to further investigate whether it is a limit cycle oscillation or the oscillation is growing up or coming down. But there is a possibility, and it is also investigated earlier, that there can be an existence of limit cycle oscillation in such cases, and in this case for a larger inductance it may end up with a limit cycle oscillation. That means, it is a sort of damping in the closed loop system of the two stage converter, where the first stage is an open loop. How to improve damping, inject damping? So, now we want to control the IBC using current mode control, and this is also reported in many literature that current mode control can provide active damping, and that we have already discussed in the context of current mode control. Now, if we go back to our simulation, and now if we change this, if we now use another current mode control block diagram, that means we just simply copy paste, we keep this somewhere here, because this block we do not need it. Okay, so it has gone down. Yeah. So, what I am going to do now, I want to use current mode control for the, so that means we need to now provide, this is the gate signal and this is my Vref 1, the first stage, and I need to connect, this should be my Vref, sorry, this should be my Vref 1, this should be my V0 1 and inductor current 1. Okay. All other blocks are same. So, I need to connect this to the inductor current, this is what, and the output voltage, okay, and then okay. So, now it is under current mode control, same configuration you are using. Okay. It is not necessary to run in the same configuration, but now we are running for the same simulation result that we obtain, which shows unstable behavior. Now, we want to run under closed loop, both the converter now running under closed loop, and we want to overlap the two simulation results by dotted curve, which is the now IBC is running in the closed loop current mode control. Okay. So, now we are running both the converter closed loop. Earlier POL was under current mode control closed loop. Now, IBC is also we are running in current mode control under closed loop configuration. And we want to see whether can we provide active damping by means of current mode control or not. So, you can see here that initially there are some startup transient, after that so it becomes stable. You can see that this is the waveform that it becomes stable. So, this is a dotted line becomes stable, whereas in both cases these inductor currents are stable. So, output voltage like both waveforms have overlap, they are overlap. So, now the current mode control is able to stabilize this converter, and if you go to the current waveform, so I will show you that if you zoom it, now inductor current becomes stable for this case. Okay. So, this IBC converter they are matched exactly. So, it is very hard to distinguish, okay, and stable. But now if it is even with a larger inductor. So, even if we reduce the inductance value, the stability property will also increase, because we have increased the inductor which became. So, now if we reduce and if we use a dotted line curve now, and we want to run the simulation again. So, now there are 3 traces. Okay. This is also closed loop, but now with a smaller inductor, which is which should provide more stability, because open loop was stable with 20 microhenry inductor, and now we want to do closed loop, and we want to see that all 3 waveform together. Okay. So, you can say that it is perfectly stable, both are again overlap, perfectly stable, and currents are also stable. So, that means the current ripple has increased because we have reduced the inductor value. So, that means now we came to the conclusion that so both the converters are running in stable periodic behavior. Okay. So, that means we can provide active damping by means of this closed loop control by current mode control. So, current mode control provide active damping, and that actually stabilize the whole system. So, in summary, we have discussed cascaded DC-DC converter, and we have used our plug and play MATLAB model to create cascaded converter from our individual DC-DC converter. We have also discussed origin of constant power load, and we have also discussed the nature of damping and also existence of limit cycle oscillation, whether it is an unstable open loop system, that also have discussed, and some possibility of limit cycle oscillation also we have discussed. And we have also discussed that the damping, active damping by current mode control can be used to stabilize the overall system. Okay. So, with this we want to finish here. Thank you very much.